everyone. Welcome. Thank you so much, Kirsten, for such a nice introduction. We're so happy to have you here tonight with us. We hope you enjoy this journey to take with GAPS. So we will be talking about the General Antiparticle Spectrometer, or GAPS. This experiment is designed to search for dark matter signatures through antiparticles. And GAPS, as we speak, is returning from its space flight in Antarctica back to Nevis. So it'll be here hopefully at the end of the month if we're very lucky. So we'll be talking about that tonight. So another longer introduction. I am Kelsey. I'm a graduate student at MIT and also at Columbia University. My first physics gig was at CERN, where I calibrated detectors. I really loved physics. I really loved particle physics, so I stayed in it. Although right after that, I switched briefly to laser engineering. This picture is from when we did disaster relief with a LiDAR for Hurricane Florence. But then after that, I decided I wanted to come back to astrophysics again. And on GAPS, I fabricate and calibrate silicon detectors. That has been really fun. I'm also very excited to be looking at flight data, which we'll talk about a little bit of. I have done a lot of building and unbuilding GAPS in many different locations.
Yeah, hi, I'm Kaliroë. So, brief introduction about me. I did my bachelor degree at University of Illinois Urbana-Champaign in engineering physics, where I actually briefly worked on a different balloon experiment called Spider. So it was always in the cards for me to be on balloons. Then I went to MIT, where I got my PhD doing a different dark matter experiment. So all of the pieces are coming together. Undergrad balloons, grad school dark matter, and now that I'm here at Columbia, I'm working on GAPS. And on GAPS, I've served as the local power systems expert while we were in Antarctica for launch. I also additionally do work on the silicon detectors, and I do some analysis work. So we're talking about GAPS, and just giving a brief outline, we'll talk first about some science background of the experiment. We'll talk about the experiment itself and how that works, and also building and testing GAPS, and finally the GAPS Antarctic campaign and launch. Okay, so starting with some science background. So the universe is composed of three major parts. Only about 5% of the universe is visible matter. The things that we can touch, we can see around us, that's a very small fraction of the universe. The biggest part is dark energy, which is the force that drives the acceleration and expansion of the universe. And the third part is dark matter, which is the topic of this talk. So we have quite a few pieces of evidence for dark matter, but I'm only going to focus on a few of them. And the first one I'll talk about tonight are galaxy rotation curves. So now if you look at a spiral galaxy and you add up all of the matter you can see, counting stars and gas and all of the things like that, you can make a prediction of how fast you think stars should be traveling at different distances from the center of those galaxies. Now you add it all up and you make your prediction, and you think it should look something like this. As you go out towards the edges, things slow down. Now in 1980, Vera Rubin set out to test this. So she went and she measured the speed of stars at different distances from the center of spiral galaxies. And what she found was that this prediction was very wrong. She found that stars were spinning much faster, much further out from the center of these galaxies. So this is an animation of what this looks like. So we can see on your right what we expect. So you see it's quite slow out on the outside there. But what we actually see is them rotating quite quickly. I mean, this is sped up. This is not actually what you would see if you looked at a galaxy, but it is relatively much faster. It's so fast, in fact, that you would expect if it was traveling this fast and that's all that was in that galaxy, it would fly apart. It wouldn't be stable. So what this tells us is there is more going on in these galaxies than what we can see. And it means they're much more massive to allow them to spin faster, and they also extend much farther out from the radius that we can see. So that tells us that dark matter exists in most of our galaxies, and it doesn't interact with the electromagnetic force. What I mean by that is these dark matter particles aren't emitting light. We don't see them, so they're therefore dark. All right, the next piece of evidence I'll be talking about is the cosmic microwave background. And so These are photons from very, very early in the universe, back when atoms first were starting to form. So we can look at this cosmic microwave background, and we can measure the temperature differences across the CMB, cosmic microwave background, and compare that on different angular scales. And that's what this x-axis is right here, and then the change in temperature is here on the y-axis. Now we can model what we think this should look like, and what we can do is to this model add different amounts of dark matter. So you can see this bar going up and down here. And as we change the amount of dark matter that's in the universe, we change what this spectrum looks like. But we can also actually measure this. So we go out and we take this measurement, and then from the measurement, we can compare with our models, and that actually tells us that we do have dark matter in our universe, and we have about 5 times as much dark matter as regular matter in the universe. And this also tells us, since the CMB formed so early in the universe, dark matter must have been around at that time as well. Okay, next piece of evidence are large-scale structures. So as you all are familiar, our universe exists in structures, right? We have our galaxies, we have our galaxy clusters, and it's not just soup. But the universe in the beginning was just soup. And now I'm sure we've all spilled our fair share of soup. And you know, as it dries, it doesn't form nice structures, right? It dries in a plain space. But we do have these nice structures in our universe. And that tells us that there was something that existed that formed gravitational potentials for the universe soup to fall into. So this is dark matter. It formed these gravitational potentials, matter fell into them, and we have the structures we see today. So the takeaway from this is that dark matter must have that ability to cluster. You have to be able to form these gravitational potentials. And that means that it can't be too fast. If it's too fast, it won't clump. So if you've heard someone say cold or hot dark matter, that's what this is in reference to. Cold dark matter is slow, hot dark matter is fast. So most models of dark matter are cold. Now, maybe you're listening to all of this and you're kind of thinking to yourself, well, you know, maybe we just don't get gravity. Gravity's weird, right? Maybe this is dark matter is nonsense and it's just that we don't understand gravity. This next piece of evidence I'm going to show you hopefully convinces you that it's not a misunderstanding of gravity. So what I'm showing you here is the bullet cluster. This is actually a new image of the bullet cluster from the James Webb Telescope. It's quite nice. You can see all the little galaxies in here. So the bullet cluster are 2 galaxy clusters that collided into each other. And now as we look at this picture here, you just see a bunch of stars and galaxies, and this is the visible spectrum. So instead, let's look at it through a few different lenses. First, we'll look at it with X-rays. So as we look at the X-ray images, the pink parts here, what we're seeing here is the hot gas from these galaxy clusters. And galaxy clusters, the main mass in them is this hot gas. So this is the majority of visible mass from these galaxy clusters. And now you can see this one here on your right has this kind of cone shape here, right? It's like a bullet. So here's where the name comes from. It's passing through as a bullet. So as these 2 galaxy clusters pass through one another, they experience some drag. And so you get this fun shape here, and they kind of slow down. But now if we look at the blue, we're looking now at gravitational lensing. So we've seen where most of the gas is, and that's where most of the visible matter is in these galaxy clusters. But then as we look at the gravitational lensing, what we're seeing is the actual center of mass of these galaxy clusters. So even though all of the gas is further back, most of the mass from these clusters is further ahead. So what happened is as these 2 clusters passed through each other, the gas experienced drag, but the dark matter did not. This is very difficult to explain with gravity. So hopefully I have convinced you now that dark matter is real. But now you might be saying, okay, but what is it, right? So we have a few different ways we look for the actual nature of dark matter. So we look oftentimes on the ground, and there's quite a few experiments here at Nevis that look for dark matter. There's the xenon experiment, which looks for collisions of dark matter in liquid xenon. There's experiments at the LHC, in particular ATLAS has a large collaboration here at Nevis, and they are trying to create dark matter and take that measurement. There's also the IAXO experiment, which looks for dark matter particles coming from the sun. Now, all of these are fantastic experiments. They are doing great science, and one day they might find dark matter, but that day is not today. So let's look to the sky, right? We found a lot of evidence for dark matter in the sky before. Let's look again. So we can look at things like stars, galaxies, clusters, compact objects. You can look for X-rays and say, if I had this type of dark matter, I would see these X-rays. And that's great. There's a lot of good science to be done here. The issue is the universe is quite complicated. So there are many, many backgrounds. There's many things that could be making all types of signals. For example, there's this very compelling signal in the galactic center, which is a gamma ray access. This could be a signature of dark matter, but it could also be millisecond pulsars. There's a bunch of fantastic scientists working on this, and they will get to the bottom of this one day. But this millisecond pulsar background is what's holding them back from saying we found dark matter. So then, what's a dark matter signature with a low background? Low energy antimatter, and that's what we look for. So why antimatter? So first I'll say antimatter particles are just the opposite charge of their matter counterparts. And antimatter is not the same thing as dark matter. Antimatter we have seen, we've measured, we've created. So when two matter particles, when a matter particle and an antimatter counterpart interact together at low energies, they annihilate, and that mass is converted to energy. So the universe is mainly composed of matter, as you see, we're all here. So antimatter is a relatively low abundance. There's not all that much of it in the universe. But which antimatter do we look for? We look for the antideuteron, which is a union of an antineutron and an antiproton. Now, these low energy antideuterons are very difficult to produce in the known universe. So they are very, very low background. Question is, how does dark matter produce them? So when two dark matter particles love each other very much, they can come together and annihilate. And from that annihilation, you get many different products. And some of those products are standard matter products, like neutrons, protons, and electrons. But you can also get antideuterons from this interaction. And those antideuterons make their way through the universe, bending through the magnetic fields, make their way all the way to the GAPS experiment, which Kelsey will tell you more about.
Okay, great. Great segue into the GAPS experiment, which is an experiment that is optimized for searching for antideuterons as a signature of dark matter. So, what is GAPS? Some of you have seen it, actually. Glad to see you back. This is GAPS, and it is our answer to the question of how to catch a low-energy antideuteron. So, for scale, this is GAPS on a crane in Antarctica, and there's a man on this crane, which you can see for scale. But for some numbers, GAPS will fit pretty nicely into a 5 by 5 by 5 meter cube, so it's quite large. GAPS is made of two sensitive subsystems. There's a plastic scintillator-based time-of-flight system, and there is a silicon detector-based tracker. I will go into what those mean in the next few slides, but additionally, you can see here in this picture that there are solar panels. Solar panels point towards the sun, and they power our instrument during flight. Additionally, there's a radiator. The radiator will point away from the sun, radiating heat, and that allows us to operate our tracker by keeping it cold. And then lastly, we have all the electronics we could ever hope for in the electronics bay. So that's for storing data and operating the instrument. And that is basically what we were able to fly and what we flew. Okay, so I'm going to go over how GAPS works with this cartoon cross-section of the GAPS subsystems on the left here. And we're going to go over this with the ideal antideuteron particle. So the ideal antideuteron particle has a speed and energy and trajectory that will result in it stopping inside of our tracker, which is perfect for us to measure it. So let's start with that. Okay, so an antideuteron that reaches a tracker will have to pass through two time-of-flight layers. The key word here is time. So imagine you're on the track and your friend is running on the track. If you measure the distance they travel and how much time it takes for them to travel that distance, you can know their speed. we do the same thing with particles, except particles move much, much faster. So when a charged particle passes through one of our very long time of flight paddles, it will produce light, and it will send that light into the different into the directions of the paddle into two different detectors on either side. When we take the timestamp of the particle as it passes through two layers with a distance that we know, we can know how fast it's going. And additionally, we also want to know its position. When the particle passes through the time of flight paddle, it will send light in both directions. When we take the timestamp at both of those ends of the paddle, by comparing the timestamps of those light detections, we can tell approximately where the particle is. This happens very fast. Light travels very fast. And the TOF is responsible for telling our instrument if an event looks interesting based on the measurements it makes. So very big responsibility for our TOF. All right. Next, the ideal antideuteron passes into the tracker. So the tracker is made up of smaller detectors. These smaller detectors are bisected into, or segmented into 8 strips each. They are much smaller than the TOF panels, and they give us a very tight measurement of position of this particle. So now we have a lot of information about where the particle is. In addition, our silicon detectors can very precisely measure energy. So these energy depositions also tell us a lot about the particle. And also, as a slow particle deposits energy, it slows down even more. And so our silicon tracker also offers as a stopping target for the antiparticle. So antideuterons have a -1 charge. So do electrons. When they slow down enough, they will ionize a silicon atom and take the place of an electron inside of that atom on its shell. And this is what we call an exotic atom. It is very unstable, and it will start to decay very rapidly. So what that decay looks like is that the exotic atom will decay and release X-rays as a result, and those X-rays will have an energy characteristic of the particle that initialized that exotic atom formation. So an antideuteron has X-rays that are 30 keV, 67 keV, and 44 keV. So after that exotic atom is formed, it will release X-rays, which our detectors are sensitive to through the photoelectric effect. And then after that, as Kaliroë mentioned, matter meets antimatter. The nucleus is full of protons and neutrons, and the antideuteron is an antiproton and an antineutron. When that antimatter and matter annihilate, E is equal to mc squared. You will produce annihilation products as a result. You'll have to conserve momentum and energy. So those annihilation products will spray out in all different directions, and many of them will be, our instrument will be sensitive to many of those. So we will be able to measure those same properties of speed and energy depositions of these annihilating products. And as a result, your footprint of an antideuteron will be that an antideuteron comes in, depositing energy, slows down, stops, creates an exotic atom that releases X-rays, and then annihilation products. And this is a very unique topology for an antideuteron. So the antideuteron is a very interesting dark matter signal. Gas is also sensitive to antiprotons, but antiprotons look very different. They have a slightly different topology to the antideuteron. An antiproton with a similar speed as an antideuteron will have different stopping depth, different decay X-rays. The exotic atom it makes will have different decay X-rays than the antideuteron, which will be measured. And additionally, the multiplicity of annihilation products will be different than the antideuteron. An antiproton, being only one antiparticle, will have about half as many annihilation products as the antideuteron. And so these footprints look very different, and we are able to measure antiprotons and antideuterons and distinguish very well between them. So lastly, I want to talk about the proton background that we see. GAPS is also sensitive to low energy protons, which is a measurement that's also very interesting to the community. So protons are charge +1 particles. It's a very abundant background by comparison, but it does not form exotic atoms, so it does not release characteristic X-rays, and it does not annihilate inside of our instrument, so it doesn't have this annihilation star. And through these different footprints, we're able to very well identify these different kinds of particles and also tell them apart. And through that, GAPS is able to detect many different particles.
Now, I'm sure you all are wondering, why do we have to stick this thing on a balloon, and why do we have to take it to Antarctica? So the reason why it's on a balloon is because as we go higher up in the atmosphere gets thinner. And in the thinner atmosphere, less particles are stopped. So we fly up, so we get more particles. Why Antarctica? So there's two major reasons why we go to Antarctica. One is the orientation of the Earth's magnetic field lines. You can see down here, they curve inwards at the poles, which means charged particles are not deflected. they come into the Earth. The second reason is that the circular winds that form in Antarctica and the fact that it's over a landmass means that we can fly for a long time and that we can recover our payload. It lands on land and we can go pick it up. But these winds are only there during the summer. And actually, the background of this slide is not quite right. That's right. It's only daytime in the summer when you're there. The sun never goes down. So for a period from about early December to mid to late January, these winds are circular. And during that time, the sun does not go down at all. So you hear us say how many days we were there. You can tell us you're wrong. You were there for less than a day because the sun never set while you were there.
Okay, so I'm going to take you on the journey of gaps before Antarctica. We're going to go all around the world building and testing gaps. Oops, no, wrong direction. Okay, so gaps started with an idea. There was a professor in Italy named Fiorenza Donata, and she's the person who we credit for theorizing the antideuteron as a signature of dark matter. And of course, GAPS is a response to that theory. GAPS is an experiment that is optimized to search for the antideuteron. So our PI, Chuck Haley, conceived of GAPS. And the first thing you do after you conceive of an instrument, of a detection concept, is you try it out. Chuck went to Japan to find for an antiproton source. He brought the detectors of GAPS to this antiproton source, and he tested out the exotic atom technique that I spoke about for the first time, and that was a huge result. Things went well. So after that, we launched PGAPS in 2012. That is a very, very small version of GAPS. It was launched and it flew for about 3 hours-ish in Japan. It was basically a small version of the experiment which proved that the detector technology would work. Okay, so GAPS, as we know it, starts its life in Boston, Massachusetts, my hometown. It started as a prototype that was basically a larger version of PGAPS, but a smaller version of GAPS, continued to work, and then we were full steam ahead in terms of building GAPS, the payload. So GAPS was built little by little, a little more in each part of the United States, starting with this early picture in Boston, Massachusetts, and then later going to Berkeley and SSL in 2023, or 2022 and 2023, to be finished with construction. And at this moment, I will take a moment to talk about building GAPS piece by piece and how all these detectors were made and how they came together, because it was a huge effort. So we received over 1,000 silicon detectors from Shimadzu, a company in Japan. They're about 4 inches in diameter. Each one of them we tested very extensively, and each one by hand was incorporated into these modules that you see up here. Each module was connected in a row. There's 6 modules for a row, 6 rows for a layer, and then 10 layers, and every single one of those modules was handmade, and every single one of those rows were integrated lovingly into the tracker one at a time by some graduate students. And then the top, by comparison, was also a huge effort. It's about 200 paddles. Each paddle has to be hand wrapped, and detectors are put on by hand on each side of the paddle. And then those detectors are also wrapped. And you wrap them because it's scintillation light that you're looking for, and you want to wrap it to make sure you're not seeing any light that isn't caused by scintillation. So it's a huge team effort to put those paddles onto the payload, and we do have to do this at every step of the integration process. So professors, postdocs, graduate students, everyone comes together and picks up these paddles and just attaches them to the instrument at every step of that journey, the journey that you'll see continued in these next few slides. Huge effort and a great team. Okay, so after GAPS was finished being assembled, the first major test was called a thermal vacuum test, and this happened at the NTS facility in Los Angeles. And the thermal vacuum test is what it sounds like. It's a temperature test with also pulling vacuum in a chamber. So the thermal vacuum test basically proves that GAPS will survive ascent and space-like conditions. If your experiment needs to fly in space, NASA needs to see that your experiment can survive space-like conditions. And instead of sending your experiment into space, you simulate space on Earth with a huge chamber. So this plot in the center shows the profile of temperature and pressure as you ascend. Pressure gets much lighter as you ascend, and temperature gets much colder. You can simulate this in this chamber by pulling the air out in order to simulate the pressure difference, and you can simulate the temperature difference with liquid nitrogen. You use that to cool your chamber, and then you can simulate a space ascent and a long flight in space, essentially, on the ground. So GAPS is a huge experiment, and the chamber was also very huge, but these factors were colliding and we barely fit in. We slid on the rails in. We had to scoot these little panels out of the way just so we can fit inside the chamber. It was very, very scary, but we did fit and we did pass. So that was very exciting. Okay, and then GAPS came back from TVAC to Nevis here, where many people saw it. We had a little Science-on-Hudson talk a few years back. But GAPS came back to Nevis for some upgrades before going down to Texas for its last test before Antarctica. And this was called compatibility testing. This was done at the Columbia Scientific Balloon Facility. No affiliation with Columbia University, it's confusing. But this was the final step in the journey before Antarctica. So at CSBF and NASA, we have already shown that GAPS works, and we already showed that GAPS will continue to work in space. The last step of this journey is showing that GAPS is compatible with the infrastructure that will send us into space, keep us in space, and allow us to talk to our instrument while in space. So we tested the antennas. This communication was successful. That means we can beam down data while we're in flight, and we can also send commands to our instruments while we're in flight, so that was very important. GAPS also tested its solar array. We produced plenty of power, which means we were able to be fully operational during flight. And lastly, GAPS was small, was not too big and not too heavy to be launched into space. Our balloon was able to hold about 6,000 pounds. GAPS was kind of just shy of that limit, so we were good to go in terms of size, weight, and power, and we passed compatibility, which means the GAPS experiment was ready to go to Antarctica. So GAPS went to Ross Island. Ross Island is a place in Antarctica where the Long Duration Balloon Facility is based, and that is, I think, the only place in Antarctica that launches 6,000-pound experiments into space. The GAPS crew from all around the world also came to Antarctica to meet, build, and launch GAPS all together.
Yeah. So probably the part you all came here for. We'll talk a little bit about Antarctica now. Okay, so in order to get to Antarctica, we first went to New Zealand. And from New Zealand, we took military planes down to McMurdo Base. So we took two different types of planes. If you were lucky, you took a C-17, which is this plane right here. And if you were less lucky, you took a C-130, which is a much smaller plane. And this is the interior of a C-130. I was unlucky at some point during this journey. Here you can see the cockpit of a C-17. They let us go up and see that, which was really cool. And so we are on this plane as us, but also we have additional cargo, which is the GAPS experiment. So Kelsey talked about how often we took the experiment apart and put it back together. Every time we took it apart, we had to transport it. And each time it's transported, it fits in 4 20-foot-long shipping containers. And additionally, the tracker is in its own container. So these huge shipping containers were on the same C-17 as us. This is one of our collaborators there, and this is Kelsey and another one of our collaborators, Field Rogers. So we're all packed on this plane all together, along with all of the food that goes to McMurdo Station. Nothing gets in and out. Okay. Most things come in and out on a plane. Occasionally there is one ship a year, and that brings things as well. But most of the food and our equipment, everything like that, comes in on planes.
Yes, I'm sure you're all dying to know what it's like working in Antarctica. So this is a picture of McMurdo Base. It's actually quite large. I was surprised by how expansive it was. So I took this picture of McMurdo Base from the top of a hill, and let's go on a quick tour of McMurdo Base. So here in these tiny buildings, well, they're actually quite large, they're just far away. In these buildings is where we lived. It was quite cozy and very warm. It was kind of like college dorms again. We had roommates. It's interesting. In the galley is where we ate. The galley staff was really, really hardworking. They were feeding about a population of 1,500, 3 meals a day plus night shift people, so they were very hardworking staff there. But also, there was a lot of fun to be had at McMurdo Base. So there were a lot of celebrations. It was a very fun crowd to be around. There were plenty of hikes. I climbed to the top of this mountain, and from the other side of that mountain. Really interesting, beautiful scenario or scenery. And then lastly, there's history. So there's this hut that Shackleton himself survived in, and those early Antarctica explorers were taking shelter in, and those were very interesting to see. Lastly, there was a volcano. Occasionally it erupted. That was a pretty interesting sight. to behold. We were able to get a really good view of the volcano from the place we worked on the ice shelf. Okay, so we had to travel to the ice shelf in order to launch our experiment, because when you launch a 6,000 balloon into space, you want a lot of space to do so. You don't want to risk hitting anything. You want to be very clear of everything. So you go out onto the ice shelf, and this is what it looks like. There were a lot of buildings on skis. It gets set up every year and taken down at the end of the season. So a lot of these buildings are on skis, and they're pulled by bulldozers into place. And for the winter, they're brought up on piles of snow so they don't get buried under the snow on the ice shelf. So that's very interesting. Two important places for gaps is where we worked. We worked in these really tall buildings called high bays, and those are on skis. I think they're the tallest buildings on skis. And this is where we ate. This is the galley. We had private chefs, so the food was super, super good. And GAPS days were basically taking place in those two locations, and then sleeping sometimes. Okay.
Yep. So there are a few challenges that come with doing science in one of the most remote places on Earth. One is snow travel. Kelsey mentioned that our work site was on the ice shelf, right? It was not in town. So every day we boarded these two vehicles, one of these two vehicles, in order to get out to the ice shelf. It was like a 40-minute ride each morning. Well, 40 minutes, and then depends who's driving. That one was sometimes 30. So to give you an idea, those wheels are about my height. Well, my height not in heels, but they're about my height. So these are gigantic wheels, and they're necessary because the roads are ice. The roads are snow. And when it gets warmer, like I said, we were there in summer, sometimes the roads will melt a little bit. And when they melt, you can get stuck in the roads, which was not fun and happened all of the time. But that's why they have tractors and things like that to pull you out of the snow. So I showed before that we put all of our shipping containers on the planes. As you can imagine, there's quite a restriction on what you can bring, because most things are coming in through those military planes. So we have to be very mindful of what we bring, both scientifically and personally. And then probably the most obvious one is weather. Now, it was quite cold down there, but so the coldest I experienced while I was there was about -15 Fahrenheit. But the cold is not actually the main issue. They give you all this gear. You'll see a lot of pictures of us in red coats. Those are we call those the big red. And we wrote, well, I wore mine not that often. After you're there for a bit, you start just being okay being cold. So we're prepared for the cold. What is harder to deal with is visibility. So there's 3 visibility conditions that we refer to while we're down there. There's condition 3, which is, you see the picture with all these shipping containers. This is condition 3. Means you can see to the horizon, there's no issues. And there's condition 2, which means snow is blowing. You can see the road. I believe it's like you can see like 10 meters ahead of you. So you can drive, but you shouldn't unless you have to. And then there's condition 1, which is this picture right here. That's one of our collaborators in condition 1. Condition 1, you cannot drive. All of the roads are snow out on the ice shelf. Everything looks like ice. So if you try to drive in this condition, you will drive off of the road almost immediately. So condition 1 means you cannot travel. So that was one of our biggest, things we had to work around was the weather. If the weather decides to do something, there's nothing you can do about it. And then the last one, this seems maybe minor in comparison to everything else, but we had restricted personal Wi-Fi. So we only had 2 gigabytes of Wi-Fi per week. And it's a fairly remote place, and you're a little bit isolated. We have our friends with us in the form of our collaborators, but it's quite isolating. So another issue we deal with is getting a little loopy. So we had a lot of instances of things going a little bit weird, and that was definitely one of the things we dealt with while we were down there.
So on the topic of space constraints, I'm going to show a quick video from the high bay of us putting together the pieces of GAPS. This was a very interesting high bay because the crane only moved in one direction, whereas in our lovely high bay at Nevis, the crane moves in 2 dimensions, which is amazing. But we had to get kind of creative and very careful when putting together GAPS. So GAPS was sent in different shipping containers, and here it is coming together. Okay, never mind. Try that again. So we work on the umbrella as much as we can, and it goes on top. So get everything done before it goes on top, because it's hard to access. Oh yeah, this is real time. Yeah, we do move this fast. Great. Thank you. Good. Okay. And then I also want to talk about testing gaps in Antarctica. So like I said earlier, the silicon tracker needs to be cooled to a temperature in space. That's done by radiating heat out into space. We don't have space. We have the cold vacuum of space at home in the form of a few chillers that use methanol. So the methanol is cooled by some chillers. They always work amazingly all the time. They never fail. And that cold methanol is then put up to cold plates, and those cold plates are attached to the radiator, and that cools down our tracker. So when our full instrument is working, we can use not an antideuteron source. We don't have that. We do have cosmic rays that come to us from the atmosphere. Muons are fast, and they travel very straight. They're kind of like an electron, but more heavy. We understand and have measured the cosmic muon flux very well, and so we can use those to calibrate our instrument. So on the right, you can see a plot of a muon basically traveling straight down our instrument, hitting a lot of sensitive material. And by looking at many of these tracks, we can tell if our instrument is aligned. And we can also use this well-known muon source to calibrate our energy, or the energy depositions of our instrument. And it also looks very cool. So.
Okay, so once our instrument is put together and it's cold tested and we've passed compatibility, we're ready to start trying to launch the experiment. So every time there's a launch attempt, we have to get up 6 hours before that attempt. That doesn't matter if the attempt is at 3 a.m. or 3 p.m. We are up and at the facility 6 hours before that launch window. And so the first thing that's done is we get there and wake up. But after that, the payload is taken out of the high bay. I have a laser pointer for this. Out of the high bay and then attached to this big vehicle. Kelsey earlier mentioned that we have to be under a certain weight to fit on this equipment. This is that equipment. This vehicle is called the Boss. And so the Boss lifts us up. And once we're lifted, on the bottom of GAPS, they attach a few additional solar panels and some ballast. And so GAPS gets lifted and it gets taken out to wait. And a lot of launching a balloon is waiting for the weather to do what you need it to. So there's two things that need to be true for the winds. The winds up high need to be going in circles. They need to be going in the right direction. And the winds below need to be so still. I think it was under 5 knots, something like that. Yeah, so super, super calm winds below, perfectly circular winds above. So we spent a lot of our time waiting for winds to do what we wanted them to. Now, you might be looking at this, you can see a person here, but you still might be wondering how tall this is. Now, the Boss, at its tallest height, is about 11 emperor penguins tall. So it's quite a tall vehicle.
Okay, and now I will talk about 12 launch attempts over 2 seasons. So these happened in 2 different summer seasons. The launch windows are very small, and like Kaliroë says, the weather basically has to be perfect for thousands and thousands of feet in order for a launch attempt to be successful. So the launch window is very small, and the winds break up very quickly, and it only happens in summer. So to go over the launch attempts of GAPS, the many launch attempts of GAPS, the first launch attempt was December 20th, 2024. Morale was very high, and we didn't launch that day because of weather. We took another launch attempt Christmas Eve. We didn't launch because of weather. Took another launch attempt Christmas Day. We didn't launch because of weather. And again, and again. January 1st, we were very lucky. We almost launched. We went to the launch pad. They started inflating our balloon. We were all excited. We were getting hopeful. And then tragically, due to weather, again, we didn't succeed. And we had to pull the balloon back down. And so I got this picture lying on this balloon. We were so close, but January is when the window starts to close. We got just a few more attempts. And then the stratospheric winds broke up. So even if we had more time on the surface, the stratospheric winds were not circulating anymore, and we wouldn't have gotten the launch and duration of flight that we wanted. So NASA took pity on us because we took every opportunity we had, and they were all canceled due to factors out of our control. So we got lucky, and we got to try again the next season. So we strapped the payload to one of the high bays. We just kept it there. It was pulled up onto that hill for the winter, and it came back down and was ready for us when we came back. So morale was a lot lower this season, so I took fewer pictures. However, there were still many launch attempts. So December 11th of 2025 was our first launch attempt of the season that we just got back from. And December 15th was another launch attempt. And December 16, 2025 was our day. But I was not convinced it was going to be our day because there was clouds in the sky. I was so not ready to launch until they started filling up our balloon. Then I got excited again, which made me very nervous. However, over the course of the day, we heard the magical words, "Give me the balloon," which is the key words for them releasing the balloon into the sky. It has this amazing sound as it unfolds. The pin came out of the boss, which released gaps, and it floated there for a little while. And then I watched from afar as gaps floated gently into the sky, and that was considered a successful launch attempt. So gaps did get the launch we were looking for after a whole year of waiting in 2 seasons.
Yeah, so GAPS had a very successful flight. So we flew for 25 days, 2 hours, and 53 minutes. And that meant we circled Antarctica twice. So the blue was our first rotation, and then we came back. We said hi to McMurdo, which is when this picture was taken, which is of the payload. So the balloon itself is the size of about a football stadium. So this is it fully inflated. And remember those giant pictures of gaps that you were seeing, and maybe some of you saw in person? That's this little white speck down here. So that tells you about how big the balloon is. It's huge. And so we flew for a long time, got some great data, and we even have some data that looks like it might be promising. We can't say anything as of yet. We're looking at the data now, but things are looking positive. And the really great thing about our 2 beautiful concentric circles is that we landed rather close to McMurdo. You're right, I am next. Sorry. Yes, we landed very close to McMurdo. So we landed on the Ross Ice Shelf. And so this is, oops, sorry, Kelsey. This is us landing here. And then we started near McMurdo Station. This was our launch. And it's only about 57 miles from the launch site, which was very, very fortunate for us. Yeah.
Okay, so we were so close to the launch site. There are different ways of recovering a payload. Some of them are in such remote places that it is impossible to get it in the same season. We got super, super lucky. They were able to just take a team out onto the ice shelf. 57 miles away in Antarctica isn't actually that far. So they took the entire payload, they put it on a sled, and they sledded the entire payload back to LDB. And you can see it here. It looked amazing. Only thing that kind of broke was a solar panel array, but that's okay, we can get a new one. But the payload looked amazing, and it was in such an easy location to get to, all things considered, so we're very happy with that. And we took the payload back into that high bay, which was still standing for our recovery, basically, and we took it apart. The solar panel array was kind of already destroyed, but we also took off the radiator. We took off all the foam. There's so much foam, oh my gosh. We took off all the top panels, and we put them away. As we speak right now, all of this stuff, the experiment is coming back up to be at Nevis, hopefully in late April if we're lucky. So the experiment it launched, it was successful, disassembled, on its way back. We have all the data that we were hoping to recover. So all things successful, all things considered.
Yeah, so after over 20 years of hard work by various GAPS collaboration members, we launched. And then we were cut down on the Ross Ice Shelf. We got 2 full rotations. You should take a look at some of the other balloon trajectories, and maybe you don't believe me when I say ours is beautiful, but ours is beautiful. And we recovered 15 terabytes of data this season that we are currently working to analyze, and will hopefully have results for you all soon. And as Kelsey mentioned, the payload is mostly intact. So if you all stay tuned, in the coming few years, we're going to go for flights 2 and 3.
So thank you so much for watching, everybody. Yes. Thank you for coming, and especially thank you to the Nevis staff for hosting us. Also, our payload stayed here for many lovely months. It was so beautiful to come up to Nevis. I love that train ride down from campus up here. So thank you, everybody. Thank you for coming.
Thank you very much.